For more than 4 decades, Voyager 2 has been traveling away from Earth. Launched in 1977, during an era when computers had only a tiny fraction of the power found inside modern smartphones, the spacecraft was never designed to operate for this long. Its original mission was to explore the outer planets. But Voyager 2 kept going. After visiting Jupiter, Saturn, Uranus, and Neptune, it continued outward into the darkness beyond the familiar planets. Eventually, it reached a region that no human spacecraft had explored directly before. Interstellar space. But getting there was not as simple as crossing an invisible line on a map. Between the Sun and interstellar space lies an enormous region dominated by the solar wind. The Sun constantly releases a stream of charged particles that flows outward in every direction. This solar wind creates a giant protective region around the solar system known as the heliosphere. At some distance from the Sun, the outward pressure of the solar wind encounters the surrounding interstellar environment. That transition is known as the heliopause. Scientists had theories about what this boundary would look like. But theories are different from direct measurements. Voyager 2 gave researchers something they had never possessed before: actual observations from the boundary itself. In 2018, Voyager 2 crossed the heliopause and entered interstellar space. Its instruments detected major changes in the environment surrounding the spacecraft. The density of plasma increased. The particle environment changed. And measurements of the magnetic field provided additional information about the complicated region where the solar system meets interstellar space. This was not a simple wall. It was a dynamic boundary shaped by competing forces. Inside the heliosphere, the solar wind dominates. Outside, the spacecraft encounters the interstellar medium. The transition between those environments is far more complicated than a simple border. Voyager 2's measurements help scientists understand that the heliosphere is not a perfectly smooth bubble. Its shape and structure are influenced by the changing activity of the Sun as well as the surrounding interstellar environment. The Sun itself goes through an approximately 11-year cycle of activity. During periods of stronger solar activity, the solar wind changes. That can affect the size and structure of the heliosphere. This means the protective region around our solar system is not completely static. It changes over time. And that matters because the heliosphere helps shield the solar system from some of the high-energy particles that travel through interstellar space. Cosmic rays are constantly moving through the galaxy. Some have enormous energies. The heliosphere can reduce the number of certain high-energy particles reaching the inner solar system. So the boundary Voyager crossed is not merely an interesting scientific location. It is part of the larger environment that surrounds Earth and the other planets. Voyager 2 also helped scientists study what happens to particles as they approach this boundary. Some solar particles can travel outward and become trapped or redirected near the heliopause. Others encounter the surrounding interstellar environment. The result is a complicated region filled with particle interactions, magnetic fields, and plasma waves. This is one reason Voyager's observations are so valuable. Earth-based instruments cannot simply reproduce the conditions found billions of kilometers away. A spacecraft has to travel there. And Voyager 2 did. But there was another challenge. The spacecraft is extremely old. Its systems were designed almost half a century ago. Its computers are primitive by modern standards. Its power supply is steadily declining. Engineers have had to switch off instruments and carefully manage energy so that the spacecraft can continue operating for as long as possible. Every transmission is therefore precious. A signal from Voyager 2 takes many hours to cross the distance between the spacecraft and Earth. When engineers send a command, they cannot immediately see the result. They have to wait. And when Voyager sends information home, scientists are receiving measurements from an environment that no human being has ever physically visited. That makes every successful transmission remarkable. The spacecraft has already survived far beyond its original mission. And it continues to provide information about the boundary between our solar system and the space between stars. But the most interesting part is what this tells us about our cosmic neighborhood. The solar system does not simply fade into empty space. It interacts with the environment around it. The Sun creates a vast region of influence. Interstellar space pushes back. Particles cross boundaries. Magnetic fields interact. And the entire structure changes over time. Voyager 2 has given humanity a direct glimpse into that transition. But the spacecraft's journey is not over. It is still moving outward. And every kilometer takes it farther into a region that remains almost completely unexplored. The farther Voyager travels, the more questions scientists have. What does the interstellar environment really look like? How does it change over distance? How do cosmic rays move through it? And what happens to the heliosphere as the Sun's activity changes? Voyager 2 cannot answer everything. But it has already opened a door into a part of space that humanity had previously known mostly through theory. And beyond that door is the real unknown. Voyager 2 crossed into interstellar space, but crossing the heliopause did not mean reaching the end of the solar system. The spacecraft continued moving outward. And that distinction is important. The gravitational influence of the Sun extends far beyond the heliosphere. The Oort cloud, a vast theoretical population of distant icy objects, may extend enormously farther than the region Voyager has reached. So Voyager has not escaped the Sun completely. It has entered a different environment. A region where the solar wind no longer dominates its surroundings. Here, the spacecraft can measure the interstellar medium directly. That environment is not completely empty. Space between stars contains particles, magnetic fields, dust, radiation, and plasma. It is incredibly thin compared with the atmosphere around Earth, but it is not nothing. Voyager's instruments have detected changes in particle populations and plasma conditions that help scientists understand this environment. One particularly important discovery involved plasma waves. These waves can provide information about the density of the surrounding interstellar plasma. Because Voyager is so far from Earth, measurements like these offer scientists a unique opportunity. They are effectively sampling the environment between stars. For the first time, humanity has instruments operating in that distant region and sending measurements back home. This has changed how scientists think about the boundary of the solar system. The heliosphere is not an isolated bubble floating through an otherwise irrelevant universe. It is part of a larger galactic environment. The Sun moves through the Milky Way. As it travels, the surrounding interstellar medium interacts with the heliosphere. That interaction can influence the shape and behavior of the region surrounding the solar system. The heliosphere may therefore be better understood as a constantly changing structure rather than a permanent shell. And Voyager 2's measurements have helped scientists investigate that structure. But there is no evidence that Voyager encountered an artificial wall, a hidden structure, or a conscious boundary. Those ideas make fascinating science fiction. The actual science is already remarkable. The spacecraft discovered that the transition into interstellar space contains complicated changes in plasma density and magnetic conditions. It showed that the region near the heliopause is more dynamic than many early models suggested. And it provided a second perspective alongside Voyager 1, which crossed the heliopause several years earlier. Having two spacecraft traveling through different locations is especially valuable. If both observe similar features, scientists can gain confidence that those features are real characteristics of the heliosphere rather than local effects. If they observe differences, those differences can reveal how complicated the boundary really is. This is how scientific knowledge grows. Not through one dramatic measurement, but through many observations that can be compared. Voyager 2's journey also highlights something remarkable about engineering. When it launched in 1977, nobody could guarantee that the spacecraft would still be functioning decades later. Its designers could not predict every problem it would encounter. As the spacecraft aged, engineers developed new ways to conserve power and keep essential systems operating. Some instruments have already been turned off. More will eventually have to be shut down. The spacecraft's radioactive power source slowly loses energy with time. Eventually, Voyager 2 will no longer have enough power to communicate. But until then, it continues traveling. And its destination is not a specific planet. There is no final world waiting ahead. Its destination is the space between stars. That makes Voyager different from almost every other planetary mission. Most spacecraft are sent toward a particular target. Voyager completed its planetary encounters decades ago. Now its mission has become something much broader. It is sampling the environment beyond the heliosphere. It is helping humanity understand what exists outside the enormous region controlled by the solar wind. And perhaps its greatest legacy is conceptual. For most of human history, the space between stars was an abstract idea. We could observe distant stars. We could calculate their distances. We could study their light. But we had never sent an instrument into the interstellar medium. Voyager changed that. A machine built on Earth is now carrying human instruments into another environment between the stars.